Work energy theorem. The work energy theorem states that the net work done on a given object is equal to its change in kinetic energy. In other words, the work done by the net force equals the change in Ke. To explain this one, let me try to put together an example. An object with mass m is being pulled by a force F on a horizontal surface that has friction. In this case, we have four forces acting on the object: the F, the normal force, the mg, and the force of friction. Therefore, the work done by the net force in this example is the algebraic sum, hear me, the algebraic sum of the work done by each one of these forces: the work done by F, the work done by Fn, the work done by Fk, and the work done by mg. Let me detail it here. The work done by the force F plus the work done by the normal force plus the work done by mg plus the work done by the friction. This is the work done by the net. That should equal the change in Ke. Notice also that the quantities are all added algebraically. They are not vectors. Each one of these quantities can be positive or negative because they are scalars. In this example here, the work done by the force F, assuming that the force F is a constant force, is going to equal the force F times the displacement times the angle made between the force F and the displacements, which is the following one. The work done by the normal force in this case is going to equal 0. And the reason it's going to equal 0 because the normal force at all times when the object is sliding is making a 90-degree angle with the displacement. Therefore, the work done by the normal force is going to be 0. And notice, anytime there is an object sliding on a horizontal surface or an inclined or a vertical surface, as long as there is sliding, the normal force is going to do 0 work. In this case, also mg does 0 work. It's not always, but in this case, mg is making a 90-degree angle with the displacement. The Fk, however, is acting in the opposite direction to the displacement. That's always true, by the way. The friction force always acts in the opposite direction of motion, which means what? The angle that is made by the friction force and the displacement is always 180, which makes the friction force always do negative work. I hope this clarifies the work energy theorem. Now, let me try to detail it a little bit more for other situations. The work done by the net equals change in Ke. Alright, the work done by the net means the work done by all the forces. I'm going to take those forces and break them into two groups. Recently we introduced conservative forces. So, there are two kinds of forces, either conservative or non-conservative. So I'm breaking this one into work done by non-conservative forces, NC, and the other group is conservative forces, equal change in Ke. We introduced it earlier that the work done by conservative forces always equal negative delta PE. Let's make that substitution. WNC, instead of work done by conservative forces, I'm going to substitute it with negative delta PE equals delta Ke. Now, let's move the like terms to one side of the equation. Leave the WNC on one side. What's going to happen now? Delta Ke, and the delta P, when you move it to the opposite side of the equation, becomes positive. And here is another equation. that is originating from the main one. So there is no difference at all between those two equations, the work done by the net and the work done by the non-conservative forces. They both apply the same way. However, when you use the work done by non-conservative forces, the only forces that you need to include under the WNC are those which are non-conservative. For now, the only conservative force that we know of is the mg. All the others are non-conservative forces. You should never include the work done by mg under the work done by non-conservative forces. The mg, or the work done by mg, is already taken care of, and it is within the delta PE. Now let's discuss a special situation where the work done by the non-conservative forces equals 0. This is a condition, okay? If the work done by non-conservative forces equals 0, what's going to happen? 0 equals delta KE plus delta PE. Instead of leaving it in this form, let me try to detail it. Instead of delta KE, I'm going to write down KE final minus KE initial. Same thing for the delta PE. PE final minus PE initial. Keep the final quantities on one side of the equation and move the initial to the opposite side of the equation. You will obtain KE initial plus PE initial equal KE final plus PE final. This is called the conservation of total energy. KE plus PE is called total or mechanical. They all mean exactly the same thing. Okay, so the total, I'm going to write it down in this form. E total or mechanical is the sum of KE plus PE. Examples of this particular situation where the work done by non-conservative forces equals 0 is when you throw an object in the air. That's a good example. When you throw an object in the air, the only force that acts on the object is the mg. And we know that the mg is a conservative force, which means there is no non-conservative forces acting on the system. If there are no non-conservative forces acting on my system, it means the work done by those forces must be equal to 0. That's not always the case. It's possible that you have forces which are non-conservative acting on your object. But what do we want them to do? We want them to cancel each other out. So the work done by some is going to cancel the work done by the others. As long as the work done by non-conservative forces equals 0, this relationship applies. And it is a very useful relationship that we going to use very often anytime the work done by non-conservative forces equals 0.